First of all, I'd like to thank your advisors for coming out, but they didn't. My name is Tewahade. This is senior projects in which we take the entire year to document our research progress, and in my special case, a slow descent of sanity. Project Summary is a four-legged robot, also known as quadruped Finland, more or less just a robot turtle. My inspiration was from this video made back in 2011. Some vaguely Korean man made a robot video called "Can You See My Robot?" in which he made a beer can into a walking robot controlled by a wheel remote. The research that needs to be done is to what type of quadrupeds are there and what do I need to know about them? What type of legs are there? What type of boards do I need to use to control these quadrupeds? Boards are these little things right here. They all run off Arduino, which is like saying a computer that runs off Windows. They are like the circulatory system of the entire robot. If you're able to think of the skeleton as the servos and 3D printed parts and the brain and or thought as the code. Need to know how putting the tin around the robot when it hits movement, would it be able to still get a full range of walking around, standing up, tilting. Basic SolidWorks and basic C. C is the programming language that Arduino uses. Technology that's needed, a 3D printer, basic construction tools, SolidWorks, Arduino, and C programming. For anyone who doesn't know, SolidWorks is a 3D modeling program that the school uses. Project objectives. First of all was to know my career path, because I don't even know what I'm doing after this. Then I needed to learn how to write and stick to a schedule. Most of the time when I start a project, it starts off like this, ends up like that. I want to make sure that didn't happen. So become proficient with the 3D modeling program, learn more about space management, which was important for this program to try to get this quadruped as small as feasibly possible to fit inside of the camera. Become proficient with C and having walking demonstration of the quadruped. Logo design. I went with very calm, basic colors of blue, gray. I probably shouldn't very basic colors of blue and gray, mainly because as long as we're not really, this project isn't as much pushing the limits of or creating new technology as much as it is taking consistent technology, existing technology, and repurposing it for a new goal. Advisors, we have Michael Hastings, he's the general mechanical guru around here. Kane, as you see previously, freaking programming wizard over there. And then Adam Powell, he has taken this class before and usually tries to, and I need his help to try and, get a more consistent, better schedule and stay on task. Benny Grabowski, usually he'd be standing right back there. I think he died in a sudden heart attack or something right now. Anyway, he's currently a mechanical engineering professor at CU Fort Collins. His previous patents had to do with biomechanical work of a small spine implant that's supposed to go in the back of your back to help you keep your broken spine to work better. While that is a biomechanical project and this one's more of a robotics project, I thought it'd still be a good match because it still has the same general ideas of getting a mechanical moving parts into a small space. Qualifications. Freshman year I took the 10-1. Yeah, last year I did participation in 2017 Denver Metro Science Fair. I won the Office of Naval Science Research Award at that place in 5 years of messing around with just general engineering. Most of that time was just using radio frequencies, basic programming, just to see what I could do with IR controls. Now this is a big step away from that because I wanted to see what else I could do or if I'm more interested in these other ideas. November timeline. Week 1 was to research quadruped legs. Now, there are 2 different types of quadrupeds. You have a mammal and you have a spider. These mammals are more like your Boston Dynamics robots. Really good at running, they can go upstairs, they're good at working through structured areas, they don't take up much space. Problem is, they are really boring to build, and also they have terrible turning radiuses. So I went with the spider. The spider was more of a challenge to shrink down because the mammal would have been fairly simple, just to have the legs full on top of one another and shrink down the box. Also, the spider gives more interesting movement capabilities, like standing like on its heels and all the good nasty goodness. So for the coax femur and tibia, the best way to see it, if you look at the camel, there's this one. The tibia is going to be your tip finger right here. It moves up and down. Femur, same thing, up and down. And then imagine that for the coax, your finger can only move left and right. It can't move up and down, left and right. So it needs to have these 3 different joints for each robot, each robot's legs. So that's going to lead up to 12 servos for the full robot over here. Next thing was to start designing robot parts in SolidWorks. I found an open source program called Hexi. And these used the exact legs I wanted them to use. The servos are close together, knit together, and the legs can be easily modified to fit my project's needs. Only problem is this one is really long, and sorry, this is the best one JPEG I have. It also has 6 legs when mine only needed 4. So to do that, I need to modify, make a new body, print the new parts. Only 1 out of the 5 prints were messed up, so it all went pretty well. This is where the actual timeline that we made at the beginning of the year and the actual timeline that went through diverged. So now it's going to be a predicted December timeline and an actual December timeline for every other month now. On December, the first 2 weeks, start robot assembly. The next 2 weeks, redesigns if needed, because I assumed it wouldn't be perfect first try was. And then over the last week to winter break, reintroduced to introduce myself to Arduino because it's been a while since I've used it. The actual first December timeline was to finish the assembly. That was all done. It was way easier than I thought it would be, mainly because I use open source program. This X right here is to keep all of these robot legs connected to the body. Then the next one was to test the ARC board. The ARC board is this guy right here. It was used with the Hexi system. As you can see, these. Yep. Where's the dot cam light? I'm an engineer, I swear.
I'm an engineer, I swear.
All right. So these little pins right here is where you put the servo into. These pins mean that it's servo friendly. Only problem with this thing is it needs to run off of the It needs to run off the promo code 2, which is made for the Hexi system. You can just type in you want X motor to move Y degrees, and then it will turn it automatically into Arduino code. This would make the project way simpler. The only problem is that this thing has maybe the memory for 4 movements, which can't get through a whole walking cycle, so not really an option. So that means I would have to hook it up to an Arduino board. The only problem with your Arduino boards is that these don't have the 3 pins that was previously mentioned. And this rail right here that you have to attach to the signal. There's 3 different wires for each servo. The ground, positive, those are just to supply power to the servos, and then the signal that tells the servo where to move, how to move it, and what else. To connect that, I use this bundle of wires. These 2 would be connected to the servos through this distributing power to all of the currently existing servos on the robot, while these ones right here that are coming through all the way here would be connected to the servo, would be connected to the board to tell it what to move. At the time, it didn't look clean. I was planning on cleaning up later, but it worked functionally. The next week, I had to make a curl and stand code. The curl code is just to make it so that when it's in the can, it curls up into the smallest ball possible so that it looks like a can and not just a robot. Google Slides does not like videos, so where's this was the original test. As you can see, the problem with this one is that it could stand. It couldn't stand. That means I tried making it go all at once. All the code was just saying, do it now, now, now. About 3 days later, I readjusted the code. Now this is the curling and standing code, in which it gets up. Now it's able to get enough momentum so that when it actually goes down, it stands up. Perfect.
There we go.
He's an engineer, he swears.
All right, so the rest of the last week of December timeline was to send the cuts to my advisor. He was up at CSU Fort Collins. So this is really simple. The square right there is the center of the robot, and these are where the legs come out from, in which I needed to cut these parts out to attach to the rest of the leg. Predicted January timeline was the first one with the first 2 weeks finished robot assembly. That was already done last week. Research Arduino servo controls are already good. These was way similar to what I thought it would be. The next 2 weeks, finished programming the walking cycle. Right now I have a standing and curling cycle. This was a poor use of time due to, or no, this was a poor planned use of time because I hadn't yet attached it to the robot. If I made the walking code before I attached it, I could have had to redo the entire thing because I wouldn't know how the camera inhibited the robot's movement. The actual January timeline was to do mid-year implementation and then clean up the robot's wiring. To clean up the robot's wiring, I just either had to cut everything down and redo it, or I had to pick up the entire system and make sure that it would look less like a makeshift pipe bomb, more like an actual robot. This piece right here was able to distribute the power and the signal throughout the entire robot, making it look much neater and less space taking up. I was able to fit the battery and all that in the space compartment right there. The rest of the January timeline, the last week, was to try to program additional movements, such as stilting, standing on its heels, just like any way to demonstrate that it could do more than just a walk. And also at this point, I was having problems with the Arduino. These problems were that at the time, I thought that these were overheating. They were overheating, but I thought for the wrong reason. I thought these were overheating because of the code. I thought it didn't have the processing power to run it all. So I went through 3 burnt servos and decided to use a different program. The code worked like this. It's like whenever you're at a stoplight. The red light, you're going to be focusing on this. This is defining the variables for the robot. It's just vocab for the machine. The yellow light is going to tell it what to do, like where are the servos attached, and the basic first movement to set it up to where it's still. And then the loop is to give everything else of walking, standing, curling, and everything else. And then to cut the can onto the tin robot and then finish the curling code and attach that to the walking code. The curling code was still going, and I hadn't been able to set up a point in which I could go and use the CNC machine at 4 columns until a little bit later. So at the time, I had focused on adding Adafruit or trying to fix up the servo problems. The entire actually took up to cut the can. I really underestimated the time it would take to do this. Eventually, after using the CNC machine, I was able to get the entire bottom of the can cut out. This would be used later to make it into little scraps to attach to the rest of the robot. And then these parts would be attached to the feet of the robot so that it would be easier to actually stand up on top of them and blend in with the rest. This is the actual rest of the cut of the robot, so that the robot will be placed right in the middle right here. One thing I hadn't thought through completely was how was I going to attach the robot to the can? Usually this was, I did with a couple of things, some adhesives or whatever, but eventually I decided I'd probably just try to use some rivets. So the rivets would be used to drill sleeves. So flip it, drill a hole, do both these pieces, and it's all stuck together. That piece right there was 3D printed to connect to the space between the X that was shown previously on top of the board. So the rest of after those were riveted in. Then the thing would stand like this. Once it was put all together, have it all right. Had a full range of movements as much as we needed at the time. So, predicted March timeline was the first, that was fairly vague when I originally made the timeline because I wasn't exactly confident in what would happen in my ability to do this, was just to program a cycle that shows off the extent of movement. Just, waving, stilts, anything like that. Actual March timeline, over spring break, figure out how to fix the Arduino heating issue because I couldn't get any work done unless I fixed the issue. Couldn't run any additional code just past the standing and curling. I realized at a certain point, I thought I was still stuck on the idea that as the processing power, I had the Adafruit, I don't know, I can gun it again, by the way. So I had the Adafruit shield. The shield for Arduino is just to give it additional functionality. This shield was supposed to give it more processing power. I added some heat sinks, thought this solved the problem. Still overheating. At this point, I've eventually realized it's not a heating issue. The issue is that it's taking too much voltage, and not enough amps. The voltage is like how much water is coming out. The amperage is the pressure of the water. I had the correct amount. I did not have the right pressure, making it so it couldn't run these additional servos. So, this left me in a pickle. The power that this thing would need is larger than the robot. I didn't really plan for that. And also, I cheaped out on the servos, used some tiny little plastic ones that used to run off these little metal gears. Eventually, those just wore down. It was no longer able to support its own weight. And due to absolutely horrible engineering on my part, this thing couldn't be taken apart without absolutely destroying it. All right. Oh no, I have like 2 months left. Got it. New plan. Start over. Okay. The entire thing speeds up a bit. It's go fast. It's all fine. Everything's fine. Everything's fine. First thing was to test the QI light motor. This is this one right here. Absolutely fantastic, servo friendly. Has these connecting right here. These 2 black cylinders on the back are capacitors that solves the amp issue. Only problem is this came all the way from Japan, and I didn't really think that the servo library was hard coded in Japanese. I can't work with that. It's not just the defined variables, it's the actual language. So unless I wanted my project to rely on Google Translate, that was down the options. Then we have the subtitle. This one, fantastic. You see these capacitors, able to run the thing servo-friendly, fantastic. Except for that thing right there. Want to know what that is? That's a Bluetooth adapter. This code cannot run unless it has a Bluetooth signal. I could make a mock signal that would be able to simulate it, but I don't have time for that, so this wasn't going to work. Okay, April. This entire time I was at least working on the code and the design for the robot in the background, which eventually led up to this thing. I tested out those final 2 journals. The predicted timeline was to make the journal, the one back there, the board, everything, this presentation, and just take those 2 weeks to, slow down, everything's done, everything's fine. In reality, I had 1 week to assemble a robot that took me about a couple months to assemble previously, and then make the final journal presentation and presentation slideshow in 1 week. All right, let's get going. So I found this quadruped on the Thingiverse. It seemed like it would work pretty well. I just had to make these small amended modifications. These curved ones right here, you're supposed to use hot water to curve them, but as you can see, they didn't really. The curved ones weren't even, they weren't reliable, and I just didn't really like them. I was able to find a new one, just 2 square pieces that you can super glue together, all stuck together. Now it doesn't need to be reliable on garbage mechanics. Another great thing to learn about this one, another great thing to learn from previous mistakes, it's super easy to take this thing apart and fix it if I need to replace any of the servos. Just take it apart, add new servo curve, put it back together. 3D printed the whole thing at home because at the time it was the end of the year and a lot of projects were probably being printed in the actual lab, so don't have time to rely on that. Then finally I was able to do the whole skeleton build. After that was done, all I had to do was actually the programming was halfway there. I was relying on something off of Arduino Nano instead of running it off of a separate capacitor bank. I decided to go with separate batteries with a voltage regulator built into the board. So now it's got enough water pressure and enough quantity of water. So originally, without it being calibrated, the thing kind of moved like a dying cat crossing the street. It was a bit of a struggle. This should just be calibration. Calibration is how where the thing originally starts off. That's oh no. Just trying to jump off, but I just can't get there, right? One day. It's my story. No.
Press the button. There you go.
So, the good turn quadrant movement is based off of 2 steps. Step, step, move, step, step, move. That's one full cycle. Now, the 2 steps right there are to rearrange the feet and arms so that when it does the whole move part, it can just physically move its legs together. One important thing about these is that these black legs right here, you have to be able to draw a triangle between each one of these legs. And as long as it's circumference, as long as it covers the center of gravity, the robot's going to stand still enough. That was all done fine. and good until it actually gets to work on top of the robot.
Oh.
I'm gonna wait a moment.
He's losing everything. He has like.
All right, so you're able to see that through this.
Engineering, my good sir. Engineering.
All right, so that twitching right there is still due to an AMP problem because it's able to run it, but it's not perfect. So you're able to see the walking cycle of step, step, move, step, step, move. Every time it goes like that. Turning is pretty similar, it's just stepping and moving backwards, same directions. While it's working on top of the robot, it actually changes the center of gravity. So while it's still able to stand up, it's not quite balancing as much as I was hoping it would be. There we go. So due to poor traction, it's not really going anywhere. It's still able to. Either way, as you see, the thing still moves, and I decided to go with an IR sensor on top of that just to pay homage to the original inspiration where we used a remote to control the original one, and also we add a little bit more flair. Now I was able to demonstrate all the things I needed. My research goals. I achieved types of quadrupeds. Research all been done. I know that downwards mammal to quadrant standard and what the variations of those are. What type of boards are there? Already gone over those. Already gone over those, and those were all lovely and great. Now I know what boards I need and what the different values of those can be. Will the tin inhibit the robot? Yes, it does. It adds additional weight, and also the leg movements are a little bit inhibited, but otherwise, it's still fantastic. Basic SolidWorks, that's all good. Basic C, already shown by that. Project objectives. No career path. It's probably electrical engineering, but otherwise, yeah, it's going good. Learn how to write and stick to a schedule. Not really. Become proficient in 3D modeling program. That's a CSWP and a CSWA. I don't get any of those. A CSWP and a CSWA is actual qualifications for SolidWorks that would probably be considered to become proficient with 3D modeling program. I didn't get either one of those, and so I can't really say I became proficient. Learning more about space management, I say I learned more about space management and was able to fit inside the robot. The basic idea, the basic can thing was still inside. The only problem wasn't exactly designed the best. Become proficient with C. Yes, the IR controls were something new that I hadn't really tested out terribly too much, and the moving servos was new, and now I feel much more comfortable programming C. Having a walking through quadruped demonstration. That's what we covered. Any questions? Comments? Insults?